All right. Well, we're at the halfway point, or at least we'll be at a halfway point in an hour, where we finally got to the real OG beefcake transformers, or we're about to get to transformers. If I have one goal for today, it's to help all of us understand how we got from what Sophia covered 2 days ago, which is turning words into embeddings, all the way to ChatGPT and GPT-3 and these large language models. And it feel as if we could have made the sequence of decisions ourselves so that we would have arrived at the same conclusions. That's my goal. So the roadmap we're going to take here is we're going to start with modern NLP, and we're just going to look at how we're going to look at the 30,000 foot level, how we got to where we are. And we're going to talk a little bit about language models. It's going to be a little bit of review from both Phoebe and Sophia's slides, just so that it's fresh in our mind, because we're going to be building language models. And then we're going to talk about sequence modeling, and then attention, transformers, then some of these really big transformers like BERT and GPT. And then finally, we talk about InstructGPT, which was critical to getting to ChatGPT. All right, first, modern NLP. Again, my goal is to feel like you could have come to these same conclusions yourself, or at least have a better understanding of the why. Because I think a lot of us maybe, we could maybe regurgitate what a transformer is or an LSTM is, and maybe kind of get the gist, right? But the kind of why was that decision made at the time it was made, and how does that sequence of decisions result in today's state of the art, I think is really important to understanding each of the models in their context. And so what I have here on this diagram here, and I really like this diagram a lot. I think we're gonna go back to it a couple times today. The green boxes, and I apologize if you're red-green colorblind. The green boxes are places we are, or places along our path to building better NLP, and the red boxes are problems we encounter that we have to overcome. And so where we started with Phoebe and Sophia this week, where we start with digitized text. We get language into the computer using some sort of encoding, ASCII, Unicode, but we have a string of characters. And Phoebe talked about what is a word and how we split words into, or split text into words, or even split words into morphemes. And Sophia talked about how we can start to add more meaning. And so the next step is we have this blob of characters, and we want to get it into tokens, things that have potentially have meaning. And so that's the process of tokenization. And we covered some of that earlier this week. Okay, so we have tokens. We have numbers that represent individual units of language, whether it's a morpheme or a word part or a sentence part or a word. Now we need to operate on computers. Computers are good with working with long lists of numbers, especially modern hardware like a GPU or a TPU. And so we need to operate on vectors, and the solution is, I think, as we framed it, pretty obvious: vectorization, which is to say what Sophia went through was how we can first start by encoding a list of words into a vector that is very poorly encoded, like a one-hot encoding vector or some other encoding mechanism. And then mechanisms like word2vec, which allows us to get into more compact embedding spaces that better capture meaning. And that's where we left off, which is that basically we've gone through the process of word2vec or some other embedding process where we have vectors that represent language units that carry some meaning. So where do we go from there? Well, I'm gonna go through this multiple times, hoping that it starts to stick, but and I'm repeating myself on purpose. But basically, we're going to need to start processing many words in a row. That's what text, that's what speech contains. And so we're going to start with RNNs, recurrent networks, as our first solution, and different versions of RNNs. And then we're going to say, okay, well, we have such a long sequence that maybe a lot of the tasks we only need to focus on bits at a time, and we start introducing attention mechanisms. And then we have problems with scale and parallelization, and we learn in the process of maybe we don't need all of these long recurrent networks after all. Maybe we can just keep the attention part and build something that scales better. And that's where we introduce the transformer, which is currently the most common state-of-the-art model for sequences, even outside of language. Okay, and then we start scaling up our data sets and figuring out how to, okay, we can, in parallel, train really long sequences, really on very large numbers of documents. We start scaling these models up bigger and bigger and bigger and getting increasingly impressive results. We see models that are different forms of language models with slightly different flavors of training, like BERT and GPT. And okay, but these language models maybe are really good at predicting the next word, what language models do, but they're maybe not good at all the NLP tasks that we want to achieve. And so we want to start better aligning these language models to do our bidding. And one paper that's been very much in the zeitgeist recently is InstructGPT from March of last year, which helps improve alignment among other papers on that subject. Okay, so language models. This is review. I just wanted to be fresh in our minds because we are going to be talking about language models almost this whole lecture. So I need a volunteer to come up, and I'm going to actually pull more volunteers later. Drew, you want to come up? All right. So you're going to try to guess the blank, okay? It's kind of like Wheel of Fortune, I guess. Once upon a time. That's crazy that you got it right. All right. Let's try it. This one's going to be harder. I'm only going to give you 2 words as a hint. Oh, this is going to be hard because he's Canadian. Nico, what is it? And. 4 score and. Don't worry about it. All right. What about this one? Twas. Does anyone guess? Twas the night before Christmas, right? From one word, we're able to guess the next word. That's normally not the case. But we all have a language mechanism in our brain. There's actually 2 language centers of the brain, one for interpreting language and one for generating it. And we don't know exactly how our language mechanism works, but it does seem to be some sort of sequence model similar to a language model. And a language model in its core is a really, really simple thing. It is just predicting words after a sequence of words. And it's incredible what you can get these things to do. And I think the idea is that most of our world can be encoded in language, whether it's a book or something else. We're going to bring up more people, so you don't worry. And yet we can do incredible things. And another demonstration I want to do. All right, I need 2 more people to come up here. All right, great. Guys, by the way, a round of applause for Mills and Daruj and Tiffany. So get in a row, okay? I'm going to show you guys just how good we all are at language modeling, okay? So this is what we're going to do. I'm going to give you a prompt, and Tiffany's going to start, and you're going to say one word, and then you're going to say a word, and then you're going to say a word, and we're going to just keep rotating through and try to keep things coherent as best you can, okay? So the first prompt is, what are you doing this weekend? So go, you start, Tiffany. I am doing a weekend outing to pizza. What did you say? Ibiza. Okay.
What's a full stop?
Full stop. Okay, stop token. All right. Round of applause for our language model. All right, and you can't just start with stop token, even though sometimes models try that trick too. All right, we're gonna try one more. Why can't dogs drive cars? So Tiffany? Because they have no driver's license. Stop token. All right. Thanks, guys. You can grab a seat. So this kind of demonstrates what's really hard about language modeling, I think, pretty well, which is that even people who have this built-in language comprehension mechanism where we are also doing sequence modeling, there is an extra part of our brain that is also making planning about the ideas we want to get out. And in fact, there's 2 types of aphasia that based on which language center in the brain have maybe a nodule, where one type of aphasia, you can generate perfectly fluid language, but you can't get out the ideas you want to say. And there's another type of aphasia where you are saying words that are semantically related to what you're trying to say, but you can't produce fluid language. And those mechanisms seem to be distinct. And similarly, we are very good now at making models, and we're going to be getting better throughout this lecture, that can produce the next word. but we also are going to have to solve the problem of making it so that you have control over those systems. So it's just a reminder, this is a review from Phoebe and Sophia's slides. So you can have language models of different sizes, and you saw earlier how that can affect the amount of information you have. Statistical language models can be as simple as some mechanism of predicting the probability of a word following a sequence of words. Markov models are models where the probability of one state is only dependent on the current state. You can approximate this with maximum likelihood estimation. So I know this review from the earlier of the week, just as a reminder, because it's going to impact everything else we talk about. All right, sequence models. So remember, the problem that we are on right now is we have to now go from just one word, which, like if we look at Mikolov, it was looking at the context window of maybe several words, but it wasn't really doing sequence prediction. It was really just trying to learn about maybe one word in like Word2Vec. And so we need to process multiple words in a row. So I want to get across this idea that's a little bit tricky, but I think it's an important one, not just understanding NLP, but other areas of machine learning, which is this idea of how symmetries imply either invariance or opportunities for simplification. And by the way, in this lecture, there's so much jargon that is thrown around that you probably encountered about transformers and these models. If I say something where you don't fully understand it, don't just stop me and ask a question, because I think if we get through this lecture, we're going to have clear sailing after this. So symmetries in data, what do I mean? I mean that there's something you can change, that you can shift, move around, and the problem remains the same. And opportunities for simplification means if there's some sort of asymmetry, like for instance, if I have a 5-pointed star and I rotate it by 2 pi over 5 radians, I still have a 5-pointed star in the exact same place, right? If I reflect a circle through its center, you still have a circle of the same size and shape. And so symmetries imply opportunities for simplification in machine learning. And simplification means you can make more expressive models per parameter. What does that mean? That means that you can, with a model of similar size, do more, or you can take your model and make it smaller and do the same amount. And so when it comes to sequences of words, what is the symmetry that we have? In a long sequence of words, we can shift by a word and we can retain the same problem, which is to say, these are all sequences of text that you plausibly could analyze with the same model. So this is probably one of the trickier ideas in here, and it's one that's glossed over pretty much everywhere. We can shift text and throw away a couple tokens at the beginning, a couple tokens at the end, and we wouldn't fundamentally need a different neural network to process them. Now imagine instead if we had a fully connected neural network where there's a special seat for every word. That's a waste of parameters. What that's basically doing is we're relearning for every word the same concepts. And so the idea behind, so translation symmetry allows us to reuse parameters, which is to say we can just build a model that operates the same word by word as it ingests them. And that allows us to reuse the same parameters each word rather than needing to train a bunch more parameters for each word seat. And this means more parameters to scale up our model. So this is the idea behind a recurrent net. And recurrent nets are normally drawn with like loops in them. But in reality, just like a for loop can be unrolled, in reality, recurrent nets are not really recurring. They're not really recursive things. I mean, nothing is really recursive. And in reality, they're just a model that is operating word by word by word with the same parameters. And when we backprop, when we learn through that network, we're updating the same parameters multiple times in the sequence. And the idea is that because text is text, a blob of text is a blob of text, let's just build one model that ingests each word individually. And here's another picture that maybe shows this a little bit clearer, which is we unroll our loop where basically the same model A is ingesting each character at a time and then outputting this hidden state, which is then used to, in the next iteration of the loop. LSTMs, GRUs, these are all specialized types of recurrent nets that you'll typically hear about. The idea behind these, and I don't want to spend too much time on it, is that you're adding basically different types of gated highways that allow information to propagate longer through your sequence. And depending on your use case, it might not really matter which flavor you use. They're not dramatically different. They're pretty complicated. But fundamentally, the idea is that you let the model learn when to let information persist. And the idea is to just give the models a little bit longer memory. But we're going to see in a little bit, there's better and simpler solutions to do that much better. Okay, so now sequence to sequence. Let's say that instead of just taking in a set of characters or set of tokens, we want to output a set of tokens as well. So the classic example might be machine translation. So we take in a sequence of words in English and we want to output them in French or something like that. Sequence models are important because they're going to motivate attention, but also when we're consuming like audio, like MFCCs, and then outputting words, that's also a form of sequence modeling. In general, transformers are sequence modeling engines, and we're going to need to go through these to get there. So this is the original paper on sequence to sequence learning. So the idea is we're going to have now 2 recurrent nets. And the first one's going to be called the encoder, because it takes the stuff that we understand, like words, and it encodes them in what's called a latent state. Latent just means hidden, like latent heat in thermodynamics. It just means something you can't completely comprehend or see. And what that means is we're basically encoding in it maybe an idea. So let's imagine, like I say in English that like I need to go home from school early today. Maybe the latent state would encode the idea of needing to go home early today. That would allow the decoder to then translate that idea into French. And as you know, like from earlier lectures, some changes in language might be differences in morphology. So we might be going from a language with a very different morphology, differences in subject, object, verb ordering. And so it might not be a one-to-one pairing of words. We might have, words with like just one morpheme per word in an isolating language like English map onto one complicated word in like German. Or Turkish, and similarly, we might have different word orderings. If you've ever translated between languages, this is pretty familiar. And so, having this latent state that encodes an idea and then decoding it again was a pretty big breakthrough. This encoder-decoder model, and you see that in other fields long before you saw it here. Here's a picture that shows it in a little bit more detail. All right, so that brings us to attention. What if we took a look at like that translation case again? Maybe when I'm translating a really long sentence, like let's say I would like to get home from school early today. However, I need to complete my assignments first, right? That's a really long sentence, and you could have a really even longer sequence than that. Eventually, even though it is true that you don't need to, you're not going to be a one-to-one correspondence word to word. There are going to be regions or areas that you might want to focus on the latent state at the decoding stage. And so the idea behind the attention mechanism was, and this is where it was introduced, is, okay, so take in your latent space and let it using a trained matrix output a mask that then allows it to basically cut off some of its own information and limit the bandwidth downstream for the information that's likely going to be best needed by the decoder. And you can learn multiple masks if you'd like. And you're basically just learning one more matrix that you're taking a dot product with that says, okay, which region should I mask downstream? And it works a lot like attention in our brain, where you're basically like, okay, right now I need to focus, keep my eyes on the road, and you block out other things. It's the same idea. It says like, right now I think these couple words, this sort of region, maybe this is a verb, I'm going to focus in this area in the latent state, and then map that onto an area of focus when you're decoding. And that was another really big breakthrough. And actually the performance of all kinds of NLP models, ranging from machine translation to other NLP tasks, dramatically improved when we started adding attention mechanisms. And so we went from this to we've jammed this extra thing in there. It's this extra matrix that allows the model to learn how to mask regions of its latent state. Actually, attention mechanisms are really, really powerful. They're really powerful. It allows the model to learn simultaneously to look at really long amounts of data, but make decisions locally as well at the same time. And that's a really big idea. Which brings us to transformers, which we've all probably heard of transformers. Maybe you've read the paper, maybe you feel that you understand how they're implemented. This is the original paper. It's an incredible paper. Attention is all you need. The idea behind it was we take this and, hey, wait, what if we just got rid of these pesky RNNs and we just kept the attention mechanism? And the reason this is a big deal, I mean, there's a lot of reasons it might be a big deal, but one reason this is a big deal is recurrent networks don't parallelize well, right? So if you have a long sequence of things that depend on each other, it's not very easy to architecturally, for instance, pipeline it over 10,000 GPUs. There's also a limit to how big the models can get. And also, for what it's worth, attention allows you to focus on certain areas of the input. So why do you need that recurrent network if you can just let the model learn how to focus globally on a long sequence of tokens? And so we're going to talk a little bit about how transformers work. But the first thing I want to talk about is, so like this, just from computer science, this is linear search, right? So we want to find a certain element in a list, and we just keep linearly jumping through the list until we find the element we care about, right? And linear search, sometimes that is the best you can do. If you have an unsorted list and no sort of indexing, the best you can do is something that's O of n, meaning that if the list is growing as a factor of n, then the amount of steps before you find your element is also going to be, on average case, maybe n over 2, right? Similarly, we might then get smart and start using something like a hash map, right? This is like a key value store, a lookup table. And what we do is we do, some math tricks so that we can very quickly in O of 1 time look up a value by its key. And this is generally applicable across computer science, because being able to do something in O of 1 time is a really big deal. Now, I mean, there's trade-offs and there's things you got to consider, but this is important for us because we're trying to do language modeling. And if you think about, let's imagine we had an Oracle language model that you give it any sequence of words, and it is able to look up the probabilities for all the other words that could follow, right? So you just have infinite space and infinite compute. You could just encode your language model as a big lookup table, where for a sequence of words you look up one more word. So that's essentially what we're trying to do with a transformer or with an attention mechanism, which is make a lookup mechanism that is differentiable. And so this is a lookup table version of this language model here, right? So we have this Markov graph that we've rewritten as a matrix or Markov matrix. And it is showing language modeling is essentially a lookup, or can be a lookup if you had it trained well enough. So by making it a differentiable object, what that means is we can use calculus on it. And the reason that's important is if we can use calculus on it, then we can use backpropagation, which is, for all intents and purposes, the only way we really know how to efficiently train neural networks. I mean, that's active area of research, but I don't know anyone who's training neural networks using something other than backpropagation. But and so that's a really big deal. And that's why, honestly, a huge percentage of the field of ML research is focused on making weird things that are discrete differentiable. And in this case, even though this was discovered by basically taking this earlier discovery, attention, which was used to augment encoder-decoder models, what we realized was, okay, well, let's just use this key value lookup trick as a vector matrix operation. So, which is our normal trick, right? Like we've already seen, like with Word2Vec, oh, let's take this thing and make it a vector matrix problem, right? So this is the meat of a transformer. So it's just 3 matrices. Every layer and every what's called an attention head is 3 matrices. And so it's a little more complicated than I promised with attention. And the main reason is we might want to have the lookup between 2 tokens not necessarily commute or be the same if you swap the 2 tokens. And so by having 3 matrices, we're able to basically retain that property. But the main idea is that we have 3 matrices that we are training. One is called the query matrix, one is called the key matrix, and one is called the value matrix. And the idea is that we're taking in an embedding, or an embedding, a sequence of embeddings, for our input tokens, so that could be somewhere from a couple hundred to a couple thousand tokens. And we're using that to generate a key, to perform a query, and then look up a value. And we're just using matrices to kind of implement that same idea. Now, there's no hashing, but like we saw earlier, a lookup table is a lookup table. And so you can use a matrix as a lookup table. And that's essentially what we're doing. But it's a differentiable one where we're ultimately getting out a probability distribution. So this is kind of what the shapes of those look like. So we have embeddings that come in with one dimension, and then we have this other dimension. So in this case, our embeddings are dimension 3, and our queries that we're generating are dimension, our embeddings are dimension 4. Our queries and keys and values are dimension 3 in this dimension, in this example. And so here's the shape of those 3 matrices. And when the embeddings come in, so remember, you can always think of any matrix geometrically as a transformation. It's just a machine that takes in vectors and spits out other vectors. And so we have this machine that's taking in embeddings and then spitting out vectors, and then taking in embeddings and spitting out vectors. And that's basically it. And that's what you're doing is you're letting it learn how to mask various regions of your input space, and then deciding what to do with that masked region downstream. And that's why it's called the transformer. It's transforming your input space into a new output space. And then ultimately that goes into a fully connected layer. So one thing that, if you're really paying close attention, this is also a sticky point that I think a lot of people have trouble when they read the paper or read the code, understanding why this was necessary, which is you've lost, by getting rid of your recurrent networks, the same concept of ordering that you had before. Like the current token that you're acting on, is distinct, but word ordering or token ordering is lost. It's more of a soup of words. And so the typical trick is to encode a little wiggle that says, I'm word 1, I'm word 2, I'm word 3. And this little wiggle, we're taking it, and most commonly you take advantage of the orthogonality of sinusoids, and your little wiggle are little sinusoids, which we talked about in the first lecture. But there's probably other orthonormal sets of vectors you could probably use as well. But the idea is you add a little, kind of a little fingerprint on each token so that the model can track ordering later. And that's all you're doing. You're adding this little fingerprint that the model can retain and carry on and use later in its processing. So this is a cartoon of the entire model. So one thing is you typically don't just have one attention model, and it is a very simple model. And so you typically have multiple what are called attention heads, which just basically means simultaneously different learned sets of key value and query matrices that all maybe do something slightly different, or some of them might look more globally, some of them might look more locally, some of them might be looking for different learned features. And you're learning several of them at a time in one layer. And then you also might have multiple layers as well. And so you can see, so in this sort of encoder decoder model that we have here, we have our inputs that get encoded. We add that positional encoding, the little wiggles, and so you got a little wiggle. And then we have our multi-head attention. What that means when you see multi-head attention just means it's our key value query matrices, that little calculation we saw done several times. And then we have this residual bit that allows information to skip the multi-head attention, which was something that we first started seeing in image models a few years earlier with like ResNet. And then you have a feed forward layer, and then you have another residual layer as well. And that's it. And then we have a decoder that works similar in this case. But that's what a transformer is. It's a lot of stuff, but it really is pretty simple. It's basically you have a sequence of embedded words. It's a matrix, right? So the number of words by how much information, the dimension of that vector that comes in. And so you have this matrix that comes in, and word by word by word, you're putting it through these 3 matrices that basically transform it into a masked region that you then manipulate further and then pass forward, ultimately getting to a fully connected neural network. And then you can do this multiple times. So you can see this is being done n times here, n times here. And so you can have multiple layers and multiple attention heads. And you can imagine how this gets big quickly. And another thing worth pointing out is that as the window gets bigger, because you have this n tokens by n tokens matrix, it does grow as of O of n squared. And so it does grow pretty quickly as you try to make these models bigger. So you add layers, you add tokens in context windows, and really soon you can build the biggest models that you've ever seen, but they do parallelize well. And that's because you're doing a lot of matrix multiplications, which we know how to parallelize, and you're operating on sequences globally, which we know how to parallelize. And that was the idea. That was the problem that they were trying to solve when Google Brain did the original paper, which is they had a lot of computers at Google. That's like one of the things that they're known for is computers. And they were like, okay, how can we use these computers? And they're like, okay, well, let's make it so that we can parallelize this better. And that was the main idea. And so I know there's a lot, I'm really trying to help weave the story of how we got here. And so we're going to review that kind of story again at the end. So BERT and GPT, these are probably the two most famous architectures for language models trained using transformers. So they're just transformers where we're trying to do the language modeling task, which is to say we're trying to predict missing tokens using one of these transformers that we just learned how to build, which is a really natural application of them. BERT and looks kind of like this. I have GPT too. It is basically you have a pair of sentences, and you are masking some of the tokens, and you're trying to predict the masked tokens. And then you are also in the original BERT paper, they're also doing other tasks along with trying to predict missing tokens. But the idea was that you just have a big transformer doing language modeling. And there's, it's a little bit different form of language modeling where you're masking random parts, and that has advantages. And BERT's a really powerful model. And the B stands for bidirectional. It is doing this both directions, so taking in tokens from the beginning and from the end, essentially. GPT is very similar. So this is comparing BERT on the left and GPT here. And so BERT is what's called autoregressive, which is again another fancy word for it just keeps adding and adding and adding on the end. So that's all that it means. And GPT has also been scaled up several times. BERT has been scaled up several times. There's many flavors of these models like Roberta that are variations on a theme. But the main idea is the same, which is pump a lot of text through a prediction task on a big transformer, and then do all the data pipelining and the parallelization so you can make these models as big as possible and make them smarter and smarter and smarter. So the last thing I want to talk about today before we review this is InstructGPT. So this is a paper from March of last year, and this is what it looks like. It looks like a paper. And here, this is from their website for the paper. So this is an example of GPT-3 compared with InstructGPT. At the time, this was also trained based on GPT-3. And the idea was, we asked, okay, explain the moon landing to a 6-year-old in a few sentences. So this is kind of like the prompts that we were doing on stage earlier, right? And the language model needs to figure out something to say, which, as we talked about, is a slightly different problem than just predicting the next word. And you can see it does it both times, but it does it better here. And this is what's called fine-tuning in machine learning. It's taking a big model and then just shaping it a little bit so it's better suited for its problem. You don't necessarily need to retrain the model from scratch, but you're tuning it, you're fine-tuning it, you're doing what's called transfer learning on it. And in the case of InstructGPT, this is the picture from their paper. The idea is you're using something called reinforcement learning, which means you're basically teaching a machine learning model to rate how good an output is. So you're basically saying like bottom one's bad or top one's bad, bottom one's good. And what they actually did is they had a bunch of people rank outputs from these sorts of models, and then they trained a model to predict how people would have ranked them. And then they used that ranking model to then do what's called reinforcement learning, where you then try to train the model to be better at predicting if it's generating good or bad reward, or really if you're trying to get it to minimize the ranking that you would have outputted. And there's other paths to doing transfer learning on these big models, and there's many, many, many papers that perform transfer learning on GPT-3 or on BERT, and that's the standard way to use those models. But this technique where they had humans actually write their preferred outputs for an input and then rank other outputs generated from models, having humans in the loop and say, hey, take this thing that's just good at predicting sequences of words and make it so that it actually gets the right idea across, so that it actually does a good job, so that it optimizes some of these things. And you can see they're comparing things like toxicity, truthfulness, hallucinations, meaning making up things that aren't actually true, but sounds syntactically true, customer assistant appropriateness. And they're basically saying, like, let's have humans to wrangle this thing, this really big model, and just shape it so it's got softer edges so that it does what we want it to do, And that's an easier problem for us to define later, which is goodness. Our language modeling task is nice because it can just consume a ton of data, but this allows us to actually make it good. Okay, so let's go back through this picture again. I'm going to go through it all the way from the beginning all the way to the end. So we get digitized text in, right? Sequence of characters, sequence of Unicode characters, sequence of ASCII characters, whatever. We got a blob of characters. We go through a procedure probably using knowledge about the language that we're parsing potentially to split it up into words or morphemes or sentence pieces, just some sort of little chunks that we can tokenize. Tokenization ultimately means turning those into numbers or indices in a vector so that we can encode them numerically. And then we take those vectors and we try to make them better. We try to get them into a better embedding space. Maybe that's learned as part of our downstream models, but it's called embedding. The reason it's called embedding is that's what it's called when you take a space in one dimension, like a cube, and then you embed it on a piece of paper in the form of a drawing of a cube, right? That's called an embedding, where you're putting one, or alternatively, you're trying to do some sort of dimension reduction where your new space is better encoding meaning, and that's what Sophia covered. So now we have many words in a row. We start with recurrence. We start with just reusing our weights, exploiting symmetry, making models smaller that can consume sequences of words instead of just one word. And then we add attention. We say, okay, well, don't look at everything at once. And then we say, okay, well, maybe we just need attention. Maybe we can build something bigger and better that way. And it turns out that works better. And then we get the transformer. And then we add more and more data. We get models like BERT and GPT on these language modeling tasks, on other big tasks too, if you look at things like CLIP. And then finally, you're like, okay, well, it's really good at predicting the next word. I needed to start doing work. I needed to start doing things like operating in a dialogue system like Grace, which is what we're going to be covering next week, operating in a speech recognition system, which we're going to be talking about next week. That's where we get to. We have these models that we can start to shape to do what we want, do really powerful things where they seem alive. All right, so that's it on my content. Before we get to the answers for the last couple of weeks, or last lecture and today, does anyone have any questions? Anything that I covered that was jargony or glossed over that you want more information about? No? All right. No questions? Any remote people questions? Okay. Probably getting up in the morning. The hardest thing about training large language models, I mean, to be honest, the largest language models I haven't been involved in training, but from what I have heard anecdotally, the data pipelining and the parallelization, the basically ML DevOps of moving around these giant data sets and preparing those data sets is probably the hardest thing. The model's not very complicated, but like moving around all that data efficiently and pipelining it in a way where you maintain the gradients in a good way, you add those together well, and that's really hard stuff. And that's why it's taking years between these big large language model papers. It's because these organizations, like one of the only things those teams are doing, and they're just trying to figure out how they can make it a little bit bigger without spending $1 billion, and that's kind of how ML often works. I mean, if you look historically, even just going way back, I mean, a lot of models that have been really successful, like ConvNets, were published 20, 30 years ago. And it's really just a compute thing that we had to wait to catch up, right? The models, honestly, were published. Like Transformers are not that groundbreaking of an idea. It's just it was the right time and place. And it's just, and if anyone who's trained an ML model, typically preparing the data set and operationalizing it is always a hard part, not necessarily always the hardest part, but it's always tricky, in my opinion. Will? Well, probably a mix of hardware and data. I think that I don't think transformers are probably the most data efficient way to build systems that understand language, but they do scale well, and therefore we've been able to affordably have them run on essentially crawls of the whole internet. But I don't think the bottleneck is I think the bottleneck is probably just a combination of compute and the amount of data we have. I mean, you really can only have one bottleneck. So if I had to pick one, I'd probably say they are limited. In their case, probably by compute. Like my guess is they are not getting through enough epochs where they really need more data. The only reason they're trying to add more data is so the model probably generalizes better, which is also important to how well it performs, which is why there kind of are two bottlenecks, but it just depends what you're trying to optimize for, expressiveness or cross domain ability to generalize, which are both important. I have no idea. I don't like spoilers, so I don't know. I mean, that's a question for people that are, I think, have more takes than me. But I do think that, we did just talk about how data inefficient transformers probably are. I mean, the truth is, when I'm a baby, I don't need to consume the entire internet to start talking. And so I think everyone agrees that it's probably at least data inefficient, depending on your worldview. Maybe you think transformers don't at all resemble the mind, or maybe they're just a really inefficient version of it. I don't really know, but I think people are going to figure out ways to make transformers smaller and more data efficient, and that will probably beget models that are, again, exploiting symmetries in the data that maybe we can't see, that maybe like the hierarchical structure of language or something, and therefore are able to be bigger with the same amount of expressiveness like we talked about earlier. But I don't know. I mean, does anyone else have a prediction about what the next big thing on this chart would be? Models that are smart enough to use external sources. I think that's a really big open problem for sure, and certainly one that we care about. Any other Sophia? Yeah, multimodal stuff like clip. I think certainly, like, if you want to reason about the world, if you've never seen an image of it or you've never perceived it in any other way but text, that probably limits your understanding. Oh, just like let GPT train longer. Yeah, I mean, I actually agree with that one. I think that's a good answer, which is like, their job appears to, at OpenAI is like publish and get attention. And so, probably they're not taking their model to the absolute limit where the loss curve isn't dropping anymore. When you're training it on that much data, I would imagine. I don't know. Is there a clear relationship between model size? So the question is if there's a relationship between model. For you think about like large language models specifically, or just in general? I mean, I think in general in supervised learning, there's rules of thumb that basically like the dimension of the size of your data set can scale roughly linear with the number of parameters. But that said, with some of these big language models, they typically publish 10, 15 different sizes of the same architecture, and there's definitely diminishing returns. And so I do think that, like, without adding any other architectural smartness, probably it's sublinear. And just, I think it's just a reflection of the fact that the model is really brutalistic. It just parallelizes really well, which is important, but probably not optimal. I don't know. I mean, it's my take though. Oh yeah, what's your take? Okay, so the take is that one problem is creating coherent plans. Is that right? Is that what? There's one thing that research group focuses on predictive coding is substitute backprop. Okay. It would be interesting to see whether in the future we'll have transformers with neuromorphic architectures. Okay, so I mean, just if you guys can't hear that, the idea is that maybe alternatives to backprops that are more inspired by the brain. I mean, there's tons and tons of papers that are both trying to prove that backprop happens in the brain, no one's succeeding, to my knowledge. And there's also lots of papers being like, okay, well, we need some algorithm that's more like the brain. Like, so, you know, Hinton had a paper in December that it was yet another take on trying to do something that is more better at replicating the brain. The other one was making plans, so forming plans. I know that Jan LeCun has said that he thinks that's a big open problem in machine learning that's the least solved, which is planning and you know, basically imagination and predicting what's going to happen in a way for when you have a large action space. Sorry, Sophia? Yeah, so Sophia's talking about, like, if you look at Cicero, which plays diplomacy, which is a game like Risk, but with a lot more talking to people and a lot more backstabbing, that you have, obviously there's a big language component, but there's also this big, you know, planning component, like you might see in like something like a chess engine or like MuZero, and it's kind of a good example of something that's a lot more sophisticated than just a brutal language model. Which I think it's a great answer and a really impressive paper that we didn't cover. Any other questions? Do you guys feel like you can? Oh, another problem is multimodal learning. Yeah, I think Sophia was saying that too. She was just saying multimodal learning in general. Or he? The person who just chatted. Yeah, and I think you brought that up too, Sophia. Yeah, basically multimodal models might be able to reason about the world a lot better than just learning about the world as just words. But I don't know. It's a really interesting question. I don't think anyone's fully answered it, but like I think we're on a good path to answering those questions. Yeah, and there even brings me into like stuff like embedding, doing like joint embedding spaces with like both the structure and the sequence and stuff, and trying to do those as multimodal and reason about the structure. And then also, like, you know, Google search functionalities that like both commit vision and joint spaces. All right. Well, Sophia, do you want to come up here actually and read your answers from last lecture? I think here you can. I don't have them in the slides. Yeah, no, grab the stick. You can have the stick and just, the microphone. So make sure to, here.
Okay, these are the questions from last time that were on the board for 10 seconds. So the first question was sort of about the potential ambiguities of language. And so you have the sentence, the astronomer that the tourist saw had a telescope, but there's more than one way to interpret this. So, well, okay, now the answers are on the board, so it's not particularly interactive, but this could be interpreted as the tourist saw a person who was an astronomer who had a telescope, or the tourist used a telescope to see Earth. Not really. Or no, maybe I did that backwards. No, yeah. Okay, yeah, and then these are the associated syntax trees, which we talked about a little bit, that you were not expected to be able to produce that, but that kind of like shows the hierarchy of how the syntactic breakdown and like the structures that you could interpret on the sentence like give the different meanings. Okay, but the next two are discussion questions, so those are more fun. Does anyone have an example of an utterance that is either grammatical but like not syntactically meaningful, sort of, you know, colorless green ideas sleep furiously style, the Chomsky example, or the reverse, something that's semantically meaningful but not traditionally grammatical? Like we talked about some examples of ending sentences with prepositions that were fine. Maybe?
much speaks in semantically meaningful and grammatically untraditional.
Great, all of Yoda's lines. Perfect. Grammatical, yeah. Yeah, I mean, and it also like, it depends on how far you want to stretch your imagination, I guess, as well, because I think both of these things are, we kind of discussed a little about how what you want to call grammatical can be nebulous, like whether you want to do it based on like rules in a book or like sensible to a mental grammar, or, you know, like the descriptive versus prescriptive stuff. And then there's also, yeah, what you know, the Chomsky example I also put up on the slides, which we didn't have time to read, but like a context in which it was meaningful. So fun stuff to think about. What? That's the
Green ideas sleep
furiously. It's green ideas sleep. No, colorless green ideas sleep furiously. Was his example of a sentence that is grammatical but not meaningful, and sort of saying how like the rules of how we combine language isn't enough to get like meaningful utterances. But yeah, then there was a competition at Stanford in the 90s for coming up with a context where colorless green ideas could sleep furiously. And this one person had this whole thing about like how he like thinks about his like ideas in a like assigns, or like he gets multiple different ideas, and then some of them are like new ideas, so they're green ideas, like they're fresh. And then he likes to sleep on ideas to consider them, but sometimes the ideas are like mutually exclusive, so they have friction with each other. So sometimes when he's, you know, sleeping on two new ideas, the colorless green or ideas sleep furiously or something. But anyways, it was cute. Would what? Idioms? Yeah, I think that's a really good one. And that's also like a really good, I mean, especially like some of them are, especially like ones where you have like double negatives, like I don't want none of that or something, but right. How, yeah.
I mean, I think you can imagine it literally raining cats and dogs. Like it does have meaning. It's just whimsical. Versus like the idea, at least in when Chomsky introduced it, was that it just literally you can't
like put it together. Like your brain can't like take that in and like put out an image or anything, or like, but like, but I think that idioms are a good way to think about the role of pragmatics as well, though, because, you know, like he kicked the bucket. There's nothing about that sentence that gives you any notion that somebody died, and so you have to know. Like it's not the parts, it's not the like mode of combination. But yeah, idioms can be weird. Let's see. Yeah, does anybody want to come up with an example of how you might use like this word embeddings for any kind of NLP task?
A lot of answers.
Yeah. For instance, we use like search functionalities in our.
Yeah. So
we use these. Anybody wants to have ideas about that?
Semantic similarity, analogy solving. You can use it to pass your NLP class.
What? Document classification.
That's a good one.
Great job. Yep, you can use them as inputs to models and for pre-training and stuff. Awesome for downstream tasks. Anyone else?
You can cluster them and get cool pictures.
Thank you, Anthony. That's great. You can put them on slides. Very important.
Yeah.
Cool. Okay.
All right. Exercises for next time. First one. All right. So we talked about recurrent networks exploit translation symmetry in text. The idea being you can shift text and it's still text and probably could use the same model. What symmetry do convolutional neural networks exploit? That's the first question. Second question, GPT-2 had a context window of 1,024 tokens. The ChatGPT, GPT 3.5, has a context window of 8,192 tokens. So the question is, how might this change the number of parameters in the model if we kept the embedding size and the number of attention heads and layers relatively the same? So it's basically asking how it scales with that. And then the last question is, why does ChatGPT seem to struggle to perform arithmetic when it can write functional code? So that seems like a bit of a mystery, isn't it? All right, well, I think that's it for today. Thanks, everybody.